We will now talk about per unit quantities or per unit system. So if you have a base voltage of 120 kV chosen, we can typically say that this can be represented as a 1 per unit, depending on where you look at. So voltage of, for example, 108 and other voltages became more like 0.9 or 1 or 1.05 per unit of the chosen base voltage. So the per unit value we can say is a quantity that defines the ratio of the quantity to its base expressed as a decimal. Here you can see a small system, and with a generator on the left hand side here, with a step-up transformer, and then you have two lines, parallel lines, transferring then power to the load side, with also a transformer here. So typically when you analyze so a small system like this, you divide it into zones. So here you can see some steps, of course, that can be useful when you do calculation. But if you take just some few steps, for example, the first you have to separate by voltage zones. And so the usefulness of the per unit system is in converting all system impedances to per unit impedances and redraw the circuit without having to worry about the different voltage levels from each transformer. And the second step here, assign base values. So the next step is that you have to choose the base values for power and voltage. And the base power will be the same for each zone. And typically we use 100 MVA as a base many times, and you can also see some programs also using 1000 MVA as a base value. But each zone will have a different base voltage. So here on this drawing you can see, of course, that we have with the generator you have 22 kV, and then on the high voltage side you have 400 kV, and on the load side you have 11 kV. In addition, you also have what we call this machine base very often. So values you have in the machine need to be adjusted to the base of the system if you want to analyze it in a system perspective. And then you have other steps, such as calculate base impedance for each zone. So for example, for line you need to calculate for each zone. But I will come back to this example a little bit later. Let's just go to then the basics for understanding more on the per unit. So for one important thing is that for single phase systems or three phase systems, where the term current refers to line current, and that's important, voltage refers to voltage to neutral. And kilowatt per amperes refers to kilowatt amperes per phase. The following formula, as you can see here, relate to various quantity. But often when we do analysis now, will be given in total 3-phase MVA and line-to-line kilovolt. To understand maybe where this equation comes from, we can imagine when you calculate the apparent power, you have the equation of the voltage squared divided by the impedance. And at the same way, see the equation 2 for the same, you have that relationship here. And we will also use that for 3-phase line-to-line and 3-phase power. So the 250 equation here shows that the per unit impedance of one element and one actual impedance divided on base impedance. So, but some confusion may arise, of course, between per unit value line voltage and phase value. Therefore, the per unit value of the 3-phase kilowatt ampere on the 3-phase kilowatt ampere base is identical to the per unit value. And that helps a lot. So, we're then 3-phase and line-to-line mean 3-phase and line-to-line. Let's look at an example here. For example, if you have on the left-hand side, you have the phase values, and then you have the 3-phase values on the right-hand side. On the left-hand side, you have the phase values. So if the actual values is 108 kilovolt and 18,000 kilowatt, we can then in 3-phase. We can look at this example. So for an actual line, as I said, you have that voltage in a balanced 3-phase set. So the line to neutral voltage is of course divided by square root of 3, and the per unit voltage will then be the 108 divided on 120, or per phase, this value, and it will be equal. So even though we have in 3 phases and 1 phase, the per unit value relationship will be the same. That will also be important when we look at the power from a generator later in the course. For total 3-phase power, same, such as 18,000 kilowatt, the power per phase is 6,000 kilowatt. So we just divide it by 3. And you can see the relationship down here that you have, it will be the same for this for 0.6. So if we interpret base kilovolt ampere and base voltage in kilovolts to mean base kilovolt amperes for the total of the 3 phases and base voltage from line to line, we find those equations you see here. And those you're probably going to use a lot. And if you see on the, typically for current you have a base value in kilovolt ampere, and then you have kilovolt line to line. And of course you need a square root here. But if you look at 254, that's maybe the most important here, is the base impedance, where you're using the base voltage, the square, divided on the base MVA 3-phase. Yeah, and we can do some changes in the calculation. So for any circuit element, we can then find the per unit impedance is the actual impedance times the base kVA divided on the base voltage squared. And you need 1000 to get the relationship correct between 1000. Which shows that per unit impedance is directly proportional to the base kilovolt ampere and inversely proportional to the square of the voltage. So that's important. You can also come to a part where you have to change the base of the per unit quantities. Therefore, to change from per unit impedance on a given base to per unit impedance on a new base, this relationship in 256 is important. So it's then calculated by you using the per unit given, and you multiply it by the given and new, or I say old and new. And you can also have base kVA, the old and the new divided on that. And then you can get the new value in that zone you're working in. So, as I said in the book, the reader should note that this equation has nothing to do with transferring the ohmic value of impedance. So, we are working in per unit. You're transferring the per unit value to another per unit value. Now, back to the example that I showed in the early. So, we have this diagram, and you need to express in per unit all the quantities shown in the line diagram of the 3-phase transmission system in the figure. So you construct the single-phase equivalent circuit, as you can see below here. Now it's given that you have to use a base of 100 MVA, so it's a system base for this conversion. The line is 80 km in length with resistance and reactance of 0.1 and 0.5 ohm, respectively, and capacity susceptance of 10 microsiemens per kilometer. So it's split equal between the ends. So now we first start with the then the divided in zones, and typically here we have 3 zones. So down you can see how we can divide it: zone 1, zone 2, and zone 3, depending on the voltage levels. So you choose then a base MVA for the analysis, and we can see here we choose then 100 MVA. For zone 1 here, we choose then 22 kV as the voltage base here, and we then have to also come up with the MVA base for that zone, and then you take the machine base divided on the system base, and you get this value. So this is now on the 500 MVA base. And we also are given that the reactance is 2 per unit value. So the reactance on the 100 MVA base is now 2 multiplied with the 100 base from the system divided on the machine base, and we get the value of 0.4 per unit. So if we now look down on the zone 1 here, you can see that you have these values. value is here. In addition, now if we move to the zone 2 value, of course we now know that the reactance of the transformer is 0.1 per unit given here. It will be a little bit more calculation if it's not given here. We can give that in another example. Zone 2, we choose standard voltage base for 400 kV, and the impedance can be calculated then based on the equation shown earlier, the voltage in squared divided by the MVA base for the line. And then you have as impedance base you have to calculate, and from this again you then can get the line values in per unit here, and you can also calculate the susceptance value total for each line here. And you're typically using a pi equivalent, so you divide it in two, it's split equal between the two ends. For zone 3 we now choose the voltage base 11 kV, you can see here, and also here the reactance is given. We have a small error I see on this calculation here. And you then want to have the load also in per unit, and you're using the apparent power of the load. Of course this is the active and the reactive power, and then you divide it on system base and you get it in per unit values. So this is a small example that you can see how we can get every values on the per unit base. And from this we can have another example later to explore this more. Now look at the one-line diagram, this subchapter. So in future chapter 3 to 5 we developed a circuit models and for the different component transformers, synchronous machines and lines. So our interest is now how to portray this assemblage of these components to model a complete system. So since a balanced three-phase system is always solved as a single phase or per phase equivalent circuit composed of one of the three lines and a neutral return, it is seldom necessary to show more than one phase. So you probably have learned in the undergrad that this had per phase equivalent circuit and a neutral return when drawing a diagram of the circuit. Often the diagram is simplified further by omitting the completed circuit through the neutral and by indicating the component parts by standard symbols rather than by their equivalent circuits. So circuit parameters are not shown, and a transmission line is represented by a single line between its two ends. We will soon have example. Such a simplified diagram I'm talking about here on an electrical system is called a single line or one line diagram. So it indicates by a single line or standard symbol how the transmission lines and associated apparatus of an electric system are connected together. So the purpose of the one-line diagram is to supply in concise form the significant information about the system. For instance, the location of circuit breakers and relays, which are there in the grid, is not so important when you're making a load study. But of course, on the other hand, when you look at stability of the system and transient conditions, then it's much more important and we need them into the system. So the information about the circuit breakers may be of extreme importance. So sometimes one-line diagrams include information about the current, the potential transformer which connect the relays to the system, which are installed for metering. The information found in a one-line diagram must be expected to vary according to the problem at hand and according to the practice of the particular company preparing the diagram. So the American National Standards Institute, ANSI, and the Institute of Electrical and Electronics Engineers, IEEE, have published a set of standard symbols or electrical diagrams. And of course this depends on are we in Europe, are we in the US, and so on. So not all autos follow these symbols consistently, especially in indicating transformers. And I'm also using different other symbols maybe than you are seeing in this book in the lectures. So here is an overview of the typical symbols that can be used from the machine to running power transformer. This is a little bit different that I sometimes use in my lectures. And then you have this is typically symbols that you can use in a one-line diagram. So it's important to know the location of points where a system is connected to ground in order to calculate the amount of current flowing when an unsymmetrical fault involving ground occurs, and this will come back to later in the course. The standard symbol to designate a three-phase wire with a neutral solid grounded is shown in figure 2 in 225 in the book. So if a resistor or reactor is inserted between the neutral of the wire and ground to limit the flow of current to ground during a fault, the appropriate symbol for resistance or inductance may be L to the standard symbol for the grounded wire. So most transformer neutrals in transmission systems are solidly grounded. Generator neutrals are usually grounded through fairly high resistances and sometimes through inductance coils. Here is a feature then of a single line diagram, and it's a little bit as the earlier example. However, now we have a generator on this side also, but you can see it's two transformer, typical line, and you have two generators here and a load. This is a way to typically can represent a power system, especially in the load flow case. To calculate the performance of a system, you also have this impedance and reactance diagrams you're probably familiar with, and we have also already looked at it. So the one-line diagram is used to draw the single-phase or per-phase equivalent circuit of the system. And here is an example of the per-phase impedance diagram corresponding to the single-line diagram we had earlier. So you typically get cases, exercise examples where you have to draw it like this. And I also showed that already when we did this per unit conversion. So here is an even simpler where you have the per phase reactance diagram adapted from the earlier one by omitting all loads, resistance, and shunt admittances. So you can, in power systems, you typically do simplification all the time to get the necessary values that you needed for the calculation you are doing. So typically in a line, the resistance is much more lower than the inductance value. So many times we can just neglect the resistance, and that's good enough for that type of calculation. And as I say, hey, if a computer is available, such simplification is not necessary in the same way. So that will help a lot. So the per-phase impedance and reactance diagram discussed here are sometimes called the per-phase positive sequence diagrams. This is also something you can look at when we have fault calculation, and also in the generator, this is typically a way to describe it.